Okay, so I want to start a new topic with you uh, today, but we're going to bring a lot of the serverless stuff with us as well, in particular the Lambda service. So I wasn't sure which title I'd give this new section, but I'm giving it its more traditional title, which is messaging. Uh, a more modern title, I suppose, would be event-driven architecture. And so there's a lab with this section as well, and this lab needs to be submitted for assessment. Okay, so let's work through some of the slides. So we're looking at a set of services from AWS which are kind of categorized as integration and messaging services. And the kind of context for this is if you think about the nature of the applications that we've been developing so far this in this module, albeit they're fairly trivial, but there could be categorized as being predominantly synchronous in nature in terms of the communication flow between the different parts of the application. The different parts of our applications were we had an API gateway, we had Lambdas, and we had DynamoDB. But the communication was between those components was synchronous, as I say. And so if from the client's perspective, when a client makes a request, now our client was just Postman, but it would more typically be a mobile app, a desktop app or something, or a web app. The client makes a request. That request is sent to API Gateway. API Gateway may do some processing of it, but it forwards it on to a Lambda. The Lambda then does some number crunching potentially, talks to a database. Database responds back. Lambda does some further processing in general, and then it responds back to API Gateway, and API Gateway responds back to the client. Now, while all of that is going on, the client is waiting for the response to come back. And that is because the communication between those various components is synchronous. In other words, the there's waiting going on between the sender of a request and the receiver, whether the sender be API Gateway sends a request onto Lambda. API Gateway is going to be waiting for the response back from the Lambda. When the Lambda communicates with the database, it's waiting for the response back before it can continue. So it's synchronous from end to end. Now, if you had a scenario where uh, a request is received by a Lambda and it needs to communicate with another Lambda. We didn't do it, but that's possible. Um, Communicates with another Lambda to do some processing, and the first Lambda needs to wait for the second Lambda before it can complete its own processing. And so there's synchronous communication going on there as well. And the upshot of it all really is that your client, uh, whether that be a mobile app or a desktop app, the client is waiting for the ultimate response back from the application. And that could be a potentially long time, depending on how much processing needs to be done. If it were possible that some of that processing could be delayed uh, for a later time, and maybe the client doesn't really need to wait for that further processing. If we could somehow achieve that, then the client gets a response back more quickly. There's lower latency. That's kind of what we're aiming for, but that's only possible if there is some part of the processing of the request that can be postponed until a later time, and the client doesn't have to wait for that processing to complete. That may not always be the case, but in many cases it is, and you've got to kind of, as an application developer, stroke designer, you've got to identify those opportunities, and when you do identify them, then you can introduce this kind of messaging uh, feature or aspect to your application's design. And so what I'm really concerned about is showing you the mechanics of how you do that when you're using AWS as your platform. Okay, so that's kind of the context for all of this. This is an image that we've used a lot when we were talking about serverless. But what I want to focus on in this section is these two services down here, SQS and SNS. They are messaging services. So in the title of this slide, I've now said that we'll look at the components of a serverless message-driven application. And the more modern name for that type of application is an event-driven application. Event-driven applications implies that there is some messaging infrastructure within the application's overall architecture. And that messaging infrastructure sits between, two compute components within your application. Compute component, in the case of AWS, would be either a Lambda or even an EC2 instance. It applies there as well. So not only is it serverless, but it's also it's utilizing some messaging infrastructure within the overall architecture of the application. I've kind of given the reasoning as to why we want to introduce messaging into our application architecture. It's because we want to try and reduce the amount of synchronous communication going on between compute components. And I am including EC2 as a compute component because, as it turns out, the messaging services that AWS provides, they've been actually around. They predate the whole serverless concept. In fact, one of the messaging services, SQS, was the very first service that AWS provided even before it provided the EC2 service. So in general, anyway, the reasoning why these messaging services are useful is to reduce the amount of synchronous communication between your compute components. Because, as I was kind of trying to get across there in my kind of introduction, if you've got too much synchronous communication going on within your application, between your application's compute components, then the ability of the application to deal with spikes in demand is affected. By a spike in the demand, if there's suddenly a rapid increase in user interaction over a short period of time, that would be what we would describe as a spike in demand. Then if there's a lot of synchronous communication going on between the compute components that are dealing with the requests, the user requests, then you're going to get you're going to get throttling exceptions being thrown by your compute components because they can deal with the volume. We talked about in the case of Lambda, if it receives too many requests and it cannot spin up more concurrent instances of the Lambda function, then what the Lambda service does is it returns a throttling exception error back to the whoever tried to invoke the Lambda. So, if there's spikes in demand, then potentially our Lambda service is going to be returning lots of throttling exception responses back to whoever the client is. Similarly, for EC2, you can't have an infinite number of parallel EC2 instances being spun up, or an EC2 instance can't deal with a certain spike in traffic. Availability kind of comes into play as well. Availability in terms of network access, because potentially, in your scenario where you've got Lambda A is communicating with Lambda B synchronously, but maybe Lambda B is communicating with some other service that's not within its own availability zone. Okay. Now, if that other service is not accessible from a networking point of view, then that means Lambda B cannot complete its processing, and so it has to throw an exception and respond back to A, and that affects Lambda A as well. Okay, so whether it be spikes in traffic or just from a network uh, network failure side, um, they're both reasons why synchronous communication is something we should try and reduce. Can't eliminate it. It has to be just reduced. Another way of kind of explaining why we should introduce messaging services is because we want to try and decouple the compute components that make up our application's internal infrastructure, decoupling them through the use of messaging. And so the messaging services, there are a number of them, but the ones that we will focus on are the SQS service, which you probably have touched on in DevOps last year. I'm not sure. Certainly would have been mentioned. We'll also look at the SNS service. We won't look at data streams that much. We'll do a tiny bit on it in relation to DynamoDB, but predominantly we're focusing on SQS and SNS and how we configure these services for a particular, albeit trivial kind of use cases, and how we provision them from a CDK point of view, and also how we communicate with them from a Lambda point of view. And so the net result of introducing messaging infrastructure are you get all of these benefits: reduced latency. Your client is no longer waiting a long time, albeit the client isn't getting the full response back from the application because some of the processing has been delayed until a later time. Increased availability, because now even though you may have some networking issues, because we're using this messaging infrastructure, and the messaging infrastructure will persist its messages for a period of time. So hopefully it will persist them long enough for the network to become available again. Reduce complexity, yeah, that's okay. Complexity in the sense that if you've got a lot of lambdas and they're all communicating with each other synchronously, then that introduces a lot of complexity when you're trying to do some debugging. Decreased dependency. Dependency is really related to this decoupling idea that I mentioned up here. Okay, so that's the context and the rationale for these messaging services. So the first one we will look at is the SQS service, simple queue service. And okay, so the 101 of using SQS is you've got two compute components, and these could be separate EC2 instances. In fact, that's what SQS was designed for originally. Well, they don't actually have to be EC2 instances. This could be a server running an on-premise server running in one organization's hardware. This could be another server running on a different organization's hardware, and these could be a customer and a producer. These two servers need to communicate with each other. We don't want the communication to be synchronous because for all of the reasons we mentioned. So we would introduce an SQS queue provided by AWS platform to facilitate communication between them. One of the compute resources is classified as the producer. This is just the terminology that we use. So the producer is the compute component that is writing messages to the queue. The consumer is the compute component that is reading these messages and processing them. The bottom image is really what we will be trying to construct, where our producer and our consumer are two lambdas, and we've got an SQSQ between them. We won't necessarily set up an infrastructure where we've got API gateway, but we know how to create this connection here. This connection is still synchronous. We can't get away from that because the API gateway doesn't know how to communicate asynchronously with a lambda. It has to communicate synchronously. Although you can have API gateway communicating with SQS, so potentially a request from your client to API gateway that can actually be directed into an SQSQ. But there are complications just when you're setting that up. But this part is the part that we're kind of more focused on, how you create that mini infrastructure. So producer consumer is the terms that we use for our two compute components. Okay, I've already mentioned that SQS actually was the very first service that AWS provided. It's classified as fully managed. Now we know that that's a byword for serverless, even though serverless wasn't around as a term back in 2006. But really fully managed means we don't have to manage the servers that are taking care of the SQSQs. There are obviously servers involved, but we don't have to configure them or maintain them. It's distributed, and I'll explain what I mean by it's a distributed queuing service in a couple of slides. And it's used to decouple your compute components, which we know at this stage. These are some of the characteristics of SQS. It's highly scalable. Now obviously there are limits, but to all intents and purposes, it scales infinitely. We can write any number of messages to an SQSQ, and it will actually persist them for a short period of time. But it has unlimited throughput, and it has unlimited number of messages that it can hold on to. It does actually persist the messages for a short period of time. By default, it persists it for messages for 4 days. You can extend that, of course. But there is an upper limit, so it's not like a database as such. Up to a maximum of 14 days. And then if messages are in the queue beyond its retention period, then the SQS service will automatically delete those messages from the queue. So that is something that you may need to configure. Low latency. Okay, so there are certain guarantees in terms of how quickly the SQS service will respond when the producer wants to write messages to the queue. And there are also low latency limits from the consumer side. There is a limit actually on the size of the message. So it's limited to 256 kilobytes. Now there are techniques for getting around that. If you actually want to have a message that's larger than that, the typical way you do it is you actually write the message to a database, and you write a much smaller message to the SQSQ, and within the SQSQ message, you would have a reference to the ID of the item in the database table, so that that's how the consumer actually gets at the entire content of the message. But 256 anyway is the upper limit for the size of a message that can be written to SQSQ. The caveats, when you read the documentation, it dares say that there may be cases, albeit very limited, where the consumer will get the same message more than once. So duplicates can occur. So you've got to be aware of that when you are coding your consumer. And it's back to this idempotency idea. Uh, Again, there are kind of techniques for dealing with that, but you do have to be aware of that. Secondly, there's no guarantee that the order in which the consumer receives the messages from the SQS service is the same as the order in which the producer wrote those messages to the SQS queue. So again, that cannot be something that your application depends on. If it is the case that the order is very important, then you can do some configuration of your queue to achieve that. But there is an impact then on these issues up here. There's a particular impact on latency. If you want to have a guarantee from the SQS service that you will receive the messages in the same order in which they were written to the queue. But there are only kind of exceptional cases where that is a requirement. So neither of these caveats are significant really, but you just need to be aware of them. So in terms of your producer and consumer, it's simple enough really. The producer writes messages to an SQS queue using the SQS SDK. So there is an SDK provided by the AWS people for essentially communicating with the SQS service. It's not that the producer is writing messages directly to the queue. It's simply communicating with the SQS's API via the SDK. And the SQS service then takes care of creating the queue internally and managing the persistence of messages and writing messages to the queue. So the SQS persists the messages until, oh yeah, so the messages are persisted in your queue until the consumer is actually responsible for deleting the message from the queue, or more specifically, it's responsible for asking the SQS service to delete a message from a queue. Other than the case where the message is written to the queue and no consumer ever reads that message, in which case its TTL will expire, and we said the default TTL is 4 days. In that case, the SQS service will automatically delete the message itself. But beyond that, it's the consumer is actually responsible for taking care of deleting messages from a queue. On the consumer side, now the thing is, right, the consumer, when a message is written to a queue, the consumer is not notified straight away that there's a message waiting in the queue for it. If that were the case, then we're simply back to synchronous communication. So the way the consumer finds out about messages in a queue is it periodically polls the SQS service, essentially asking it, are there any messages in a particular queue? And the SQS service, what it does is it responds with batches. It's always a batch response that it gives back to the consumer. Even if there's only one message in the queue, the consumer has to interpret the response as being a batch, albeit a batch of one. And we'll see evidence of that when we look at the consumers, how it receives these messages from SQS. So the first thing is this idea of the consumer is actually polling, and you can configure obviously the frequency of the polling. It receives a batch is the second important point, and the third point, which I've already alluded to, is that it is responsible for asking SQS to delete the message. Now, uh, this is just a visual kind of representation of your typical flow of execution or your communication between your producer and consumer when, let's say, it's lambdas are our producers and consumers. So this is our producer Lambda. Now it is communicating synchronously with SQS for the purpose of writing messages to a queue, and the SQS service will respond when it has written the message to the queue and it is happy that the message has arrived in the queue, if you like. So that is synchronous, admittedly. The communication here is pole-based, as I was saying. But if you look at the communication flow between your producer and consumer, then it can be classified as asynchronous because in the sense that this lambda here is not waiting for this lambda to process the data contained in the message. That's why we say this is an asynchronous communication flow. From a security point of view, uh, there is what's called in-flight encryption automatically taken care of by SQS. Uh, In-flight means because the Lambda and your SQS queue are the communication is over a network, but the SQS service will ensure that the transmission of the message will be encrypted in encrypted form. The message, when it's persisted in the queue, it's also persisted in an encrypted form. And similarly, there's encryption going on here. So lots of guarantees from a security point of view. And then you have your usual kind of access control issues. So when the producer needs to have certain IAM permissions in order to write to the queue, and similarly, the consumer needs to have IAM permissions in order to be able to read from the queue. You also have what's called SQS access policies. If the queue is configured in one region and you have an account in another region that wants to be able to access that queue, then you need to set up the necessary SQS access policies to achieve that. We won't be looking at that side of it though. Simple demo. So the demo I'm going to be using just the AWS CLI as my producer. It's going to be writing messages to a queue, and I'm going to have a Lambda as the consumer. Now, when I showed you, if I go back to here, when I showed you this, right, the impression that you would get from it is that the Lambda itself is responsible for polling the queue. We actually have to program that ourselves. And in fact, that's not really how it works behind the scenes. It is the case here, right, that the Lambda is responsible for communicating with SQS, but this Lambda here does not actually communicate directly with SQS at all. It's the Lambda service that manages the Lambda, and we kind of might think of the Lambda service as being that box that's kind of managing this Lambda here. So that's what I'm getting at here, right? So we have our producer. Okay, it's not a Lambda in this case, it's just the CLI. So it is communicating directly with the SQS service, sending a message to it and asking it put a message into a particular queue. On the consumer side, it's the Lambda service. It's actually doing the polling, carrying out the polling operation. And whenever it gets a response back with a batch of messages, then the Lambda service invokes the consumer Lambda, passing it the messages, but the messages are wrapped inside the event object that this Lambda receives. And we know now that when a Lambda is invoked, the handler function, if you remember, The first parameter is the event parameter. Now, in this case, the event parameter will contain within it the batch of messages that were received by the Lambda service from the SQS service. So again, this Lambda doesn't actually communicate directly with the SQS service at all, although it needs to have the permissions uh, that will allow the Lambda service to do the polling for it. Okay. And I think that's, oh yeah, and the other side of it is, so the Lambda service polls SQS. SQS responds with a batch of messages. The Lambda service invokes the consumer Lambda with the batch. And when this Lambda finishes its processing of those messages, whatever that involves, then it's actually the Lambda service that asks the SQS service to delete those messages. Because we did say the consumer is responsible for uh, the deletion of the messages. So the Lambda service, though, will take care of that. So again, there's no code inside here that's concerned with requesting the deletion of the messages from the queue. The Lambda service does that for it. Of course, if this Lambda happens to throw an exception, or for whatever reason it cannot complete the processing of that batch, then in that case, the Lambda service is not going to request the deletion of them. And we'll talk a little bit more about that scenario later on. Okay, so I guess all we need to look at is the CDK code to create our queue and to somehow link up these two. And I think that's the next slide. Yeah. So simple enough, really. That's how you create request the creation of an SQS queue. Now there are some configuration options associated with creating a queue, and we'll see some of them later on. But for now, it's simple enough. We're accepting all of the default settings for our queue. Just give it a name and attach it to the current stack. Here's my consumer Lambda. It's just the standard configuration. There's no evidence from looking at this that it's interacting with an SQS queue. Yeah. This is the important part, really. This is how you form the connection between the Lambda and the queue, and in particular, how you indicate that the Lambda is a consumer for the queue. So you create, in the language of the CDK, you create an SQS event source. Because if you think about it, when we started talking about Lambda on day one, we said Lambda is an event-driven compute technology. And that's still the case, and I've kind of explained that in the previous slide. So here, what we're kind of describing is the nature of the event source that will ultimately trigger the execution of our Lambda. So create one of these guys, and then this is how we hook it up to our Lambda. We're adding an event source of this type. And that's it, really. All I'm doing here is I'm outputting the URL of the SQS queue. And the reason I'm doing that is because I want to use it in my AWS CLI invocation. Here the event source. Yeah, that's okay, I think. So this is the AWS CLI command that we're going to use, and we'll do a quick demo in a minute to write a message or publish a message in the queue. Here's my consumer, and it's not really doing any processing as such. The only important thing to note is that, it receives some sort of an event, And there is a property inside in the event called the records property that's only going to be there when the event is an SQS related event. And the records property is an array, and that array really corresponds to the batch of messages that has been received from the SQS service. So that's why we've got our for loop here. We need to iterate over that array. And as I've already said, it's always going to be an array. Even if there is only one message, you still have to process it as an array. And I'm not doing anything interesting other than console logging out the actual body of the message itself. Okay, so I've already deployed this application, and let's just go to CloudWatch first and do a cleanup. And let's send a message. So here's the deployment, the result of the deployment. Here's the URL of the SQS queue so that I can use it in my AWS CLI command. And so if I just use this command here, I need to change this. Okay, and if I go back to CloudWatch, there should now be a log group for my consumer. And here it is here. And if I go into the log stream, this is the first console log where I console log the actual event itself. And here we can see the records property within the event, and the records property is an array. So here's the first message. Okay, lots of stuff in it, but the only thing we're really interested in right now anyway is the body. And the body contains the hello world, which was the message that I sent to the message, the body of the message that I sent from the CLI. So that all kind of adds up. If we take a quick look at the Lambda instance itself, so here's the Lambda function, my consumer. And the only thing that's might be kind of vaguely interesting is if we look at the permissions uh, assigned to it. If we go into the configuration and permissions, you might remember that there's an execution role created by the CDK for each Lambda. Here's the execution role, and if I drill down into it, and it looks like it has two policies attached to it. The first policy is the standard policy, the default policy that allows my Lambda to write to CloudWatch logs. There is a second policy which was dynamically created by the CDK, and if we go down into that policy, then here's the actual JSON representation of the policy, and you can see it's all about giving my Lambda essentially read permissions on the queue. Okay, so the Lambda still has to have those permissions to allow the Lambda service to do the polling for us. Okay, now this policy was actually created by the CDK because of this stuff here. Okay, so that's a byproduct of these two lines of code in my CDK. It caused the CDK to create that policy and add the permissions to that policy. And that's kind of classic CDK stuff. Two simple lines of code generates a number of resources behind the scenes. The resources in this case being an IAM policy and attaching that policy to, in this case, the execution role of the Lambda. Okay, that's the 101 of how we hook up a Lambda to an SQS queue from a consumer perspective. All I'm showing you here is just a screenshot from CloudWatch logs, and I've already highlighted the fact that the event that the consumer Lambda receives, contains this record property, etc., etc. So we've explained that. Typically, though, your message is going to be something more complex than a simple string. And typically it might be a JSON structure. So when the SQS service receives a message from the producer where the body of the message is a JSON structure, then what it will actually do is it will serialize or stringify that JSON structure before it writes it to the actual physical queue. And we need to be aware of that because when our Lambda consumer receives the message, it will be in serialized form. So the Lambda does need to parse it, just using the JSON.parse method call. Okay. And I'm showing you here a screenshot from CloudWatch logs for a Lambda consumer where the message was a JSON structure. And we might just do a quick demo of that. So what I've done is I've got a simple message here. That's not what I want, sorry. this guy. So that's my JSON structure, and I want to send that to my queue. So if I go back to the README, shows me how to do that. So this is how we're going to do it. We can just actually refer to a file, and I need to change this though. So AWS SQS send message, the URL of the queue, the body of the message referring to a file. Okay, that's all we need. And again, the only thing we can look at maybe is the log stream for the consumer. So if we go back to CloudWatch logs, yikes, what am I getting here now? I'm not sure where all those come out of. Where is it going to? Oh, I see. I'm in the wrong region. You can see there in the top right, it's certain, for some reason it has switched over to the North Virginia region. I need to bring it back. And again, if we just look at the console log of the event parameter, and again, it was a single message, but you can see here the body of the message is a serialized version of the JSON object. So all we need to do is just invoke JSON.parse on the body to convert it into a JSON structure that we can deal with within our TypeScript code. Okay, that's that. What am I showing you here? Oh yeah, so here, this is where we're just doing the parsing of the serialized JSON structure. Now, when I started talking about SQS, I said it was a distributed queuing service. And so what actually happens, and this is a little bit like how DynamoDB works, in that it's distributed as well, but this image is taken straight out of the docs, the AWS docs for SQS. And so when you create a queue, um, what the SQS service does is it actually makes multiple copies of that queue across different nodes within its network. And so that's what we're kind of seeing here. Uh, so it does actually replicate the queue across a number of nodes. And when a consumer, now something I didn't mention when I was introducing SQS, because we did say SQS was the very first service and it predates all of this serverless stuff, etc., etc. But originally, the SQS service, you could have multiple producers and multiple consumers. And on the consumer side, the way the queue worked was one consumer might request a batch of messages from a particular queue. It receives those messages. The other consumers for that queue would never then actually see those messages. And that was uh, the way that the SQS queue was meant to work. If you wanted the case where you have multiple consumers and you want each consumer to receive all of the messages in your queue, then don't use the SQS service. You should use something called the SNS service, which we'll talk about in a later lecture. Uh, but so let's just conveniently ignore the fact that you can have multiple consumers, because I don't want to get into that detail. Typically, we would only have, certainly in a serverless architecture, we would only have one consumer for a queue, and that would be a Lambda. So the Lambda here, the Lambda consumer, when the Lambda service polls the SQS service for a batch of messages from the queue, what the SQS service does is it selects a subset of the nodes that are storing messages for that queue based on some algorithm. And so in this example, let's say that it's the grayed out nodes, this one, and this one. They're the three nodes that it selects, and it asks each of those nodes for a batch of messages from the queue. Now you can, if you look at the detail of the actual messages, and they're kind of labeled A, B, C, D, E for convenience, then the messages will be replicated across these different nodes. So each of these nodes is going to respond with a batch of messages, and there will be duplicates in that response. SQS will take care of removing those duplicates, and then ultimately it will send the set of messages that it received back to the consumer. The white nodes in this case were not selected by SQS. And so I think if you look at the detail, message E here, which could have been included in the response, was not included because the grayed out nodes don't happen to have a copy of message E. And that's kind of alluding to this idea of the ordering, and is not guaranteed either, even though it would have been naturally. So it would take another polling request from my consumer before it actually received message E, and the SQS service would have had to select this node. So ultimately, or eventually, it will get message E, but it may not get it as quickly as if the queue had been just stored in one node. Of course, the problem with just storing the queue in one node is we're back to the availability problem. If that node happens to be unavailable from a networking point of view, or the SQS server that's running on this node is overloaded with requests because there are other queues being stored on that node and all of that, right? But the overarching point is that the SQS service, it does actually perform distribution uh, behind the scenes, and that is uh, for um, for resilient purposes, and also the fact that it doesn't actually it decreases the possibility of messages actually being lost. And there's some detail here. Is there on the no, I'm just explaining the general workings of the SQS service internally. So that's just an interesting kind of by the way. Lambda consumer scalability. Okay. So going back to the kind of scenario that we're familiar with, which is our SQS queue and our Lambda service polling SQS for messages. Now it receives back a batch of messages. Now automatic or by default, what the Lambda service will do is it will actually create a number of micro VMs and load the micro VMs with your Lambda consumer and distribute the batch. In other words, send some of the batch to one of the micro VM instances, another subset of the batch to another one of the micro VM instances. And all of the reason behind all of that, of course, is to speed up the processing of the batch that it received from SQS. So that's how scalability on the consumer side is handled behind the scenes by the Lambda service. I think by default it starts with a minimum of 5 concurrent Lambda instances. So even though it might only receive, let's say, 20 messages in a batch, it would still spin up 5 micro VMs and distribute the 20 across the different instances. And there's no guarantee as to, what messages are received by which of these instances, and they don't have to be in order, in any particular order either. So, and then, so it starts with a default of 5. You can configure it. You can say, I never want more than 3 concurrent lambdas being spun up by the Lambda service because you know that the volume of messages that it's going to be receiving is small enough for 3 concurrent lambdas to deal with. Even in spikes, 3 would be enough. But if you don't specify a limit, you don't configure it, then potentially, where do I say it? Do I mention? Oh yeah, I'm saying down here, right? It will actually keep scaling up the number of concurrent uh, micro VM instances up to a maximum of 1,000 concurrent micro VM instances if the volume of messages is such that that is needed. And of course, the 1,000 is that upper limit that AWS have enforced on each AWS user account. Yeah. So again, you probably would need to keep an eye on that in a real world situation so that you don't let the Lambda service spin up too many of these concurrent instances, even in the cases where there is a high volume of messages to be processed. And again, that's kind of a tuning aspect to application design, which admittedly we're not looking at in detail. So that's the high level kind of view of how scalability of your Lambda consumers is handled by the Lambda service by default and automatically, subject to your configuration settings. To give a demonstration of that, I've got a second demo, and maybe just while I explain the demo, I'm just going to deploy it. Now, the purpose of this demo is to illustrate, in as much as I can, really, the scalability that happens over here on the consumer side. Although it is kind of subject to um, whatever is happening in the Lambda world in a particular region at any particular point in time. I said there on the previous slide that by default it scales. It will create a minimum of 5 concurrent Lambda consumer instances. But if there happens to be a lot of activity in the Lambda service in a particular region, when you're trying to demonstrate this, then it may not scale up to 5, but it will certainly go beyond 2. Anyway, so the scenario is I've got a Lambda over here, which is my producer, but really all it is sort of a test harness. It just dynamically creates a batch of messages and writes that batch to a queue, and then I have the consumer over here. This Lambda does need explicit permissions to write to the queue, so that's what I'm getting at here. And again, it's very like the way we do it when we were dealing with DynamoDB. So there's a convenient method that will just essentially create the IAM policy behind the scenes to allow the Lambda on the left, the producer, to write to the queue. Um, just some code excerpts. So on the top left, this is all from uh, the the producer now in this scenario, which is my generate orders. So I'm just dynamically, okay, I've just got some data types um, for convenience. So that's the structure of an order. We can ignore this stuff for now. It's not being used in this example. It'll be used later on. Uh, I've got this code here is just dynamically generating, it looks like an array of 10 orders. Okay. And here's the actual handler itself, the producer handler. And it's what I've decided to do. Maybe if I switch over to VS Code at this stage. So here's the generate orders Lambda. Okay, so we have that. So I've got an empty array of orders. Generate them. I can ignore this stuff for now. And the way I send the orders, you first of all have to wrap the orders as messages. So that's what I'm doing here, I think. Let's see, I'm mapping over my array of orders, and the output of this map is an array of these things, an array of send message batch. What do I call it? Request entries. Okay, quite long-winded, but essentially this is an array of SQS structured messages. Each SQ, each message has to have a unique ID, and I'm just using a library to randomly generate an ID for me. The V4 is this guy up here. So it's just a convenience library. And then the message body. Okay, so that's the structure of an actual message that SQS expects. Now, I could send the messages individually, but there is SQS, the SDK for SQS does provide uh, a way of sending a batch of messages to it. And so that's really what I'm doing here. Okay. So ultimately I'm sending, and it's the same kind of pattern again. It's these kind of command objects. So in this case, the command is send message batch command, yeah, and giving it my array of messages. So that's how I send them. What I'm showing you down here actually is if you did want to send the messages individually, then it's just a different command object that you create for each message and send them individually. So that's just there for uh, illustration purposes, but I'm not actually using it. That's fine. That's the producer side. The CDK code, no real surprises there. Here's my queue, no special configuration of it needed. Here's my producer or my generator lambda. Sorry, it's not. Here's the consumer lambda. The consumer lambda doesn't do anything interesting, I think. Not really. Let's see. Sorry, wrong one. This one. It just iterates over the array and okay, it is doing some validation here. We could ignore that for now. That will become relevant later on. Essentially, it's just iterating over the batch of messages and console logging out. Console logging out. Console logging out the name of the customer for the order. Maybe if I just quickly go back and look at the generation one, this guy here, my customer names. Here's where I'm creating the array of orders, and the customer names are going to be user, and then I'm using the iteration variable I uh, as the suffix for their name. So it'll be user 0, user 1, user 2, etc., all the way up to user 9. They're going to be my customer names. That'll become convenient because when I'm console logging out the customer names, I can get some idea as to the ordering of the messages that have been received by the consumer. So for now, we can ignore this kind of stuff here, right? We're not interested in that. Okay, the CDK code, create your queue, create your consumer, create your producer in this case. Connect up your consumer to its event source, which is our SQS event source. Give the producer the permissions to write to the queue, and then I'm just outputting in this case, I'm outputting the producer's name because I'm going to trigger that lambda from the command line. That's how I kick off the execution of this demo. So that's what I want to do next. And we know how to invoke a lambda from the CLI. We've done that before. So all I need to do is to change the function name. Okay, just to be super clear, I'm going to use the CLI to trigger this Lambda. It's going to generate a batch of orders. It's going to wrap each of those orders in an SQS message, sends those messages as a batch in this case rather than individually to SQS. SQS will persist the messages in the SQS queue. And on the consumer side, my Lambda is going to poll SQS for batch of messages. And then it's going to create a number of instances of the consumer to deal with the batch. Rather than giving all of the batch to one consumer, it's going to create some number of concurrent instances. Did I change the queue? No, I need to grab the queue name, or sorry, the Lambda name. Before I hit return, I want to check my CloudWatch side. Do clean up anyway. Under response, and if I do a refresh here, now there's going to be, this is the log group for the producer, might generate orders. There's going to be a delay before I see a log group for the consumer because of the kind of polling delay that's introduced. Okay, but it's there now. So this is my consumer log group. And in this case, okay, looks good. It looks like it. So there's a log stream for each instance of my consumer, and it looks like there was one, two, three, four instances in this case. Four concurrent micro VMs were spun up by the Lambda service. And if we just look at maybe one of the two of them and just see what messages did it receive. So let's see if we start. So that this one is just going to be the console log of the event itself. So you see the first message it got in the subset of the batch was message 6 really because it starts at user 0. So that's kind of an indication that there's no guarantee of the order in which the messages are received by the consumer. Then it's 2. Okay, it's a very good example actually. So it got message 6 first, then it got message 3 because it begins at 0, and so on. Then it got 3, and is that out? So it got 3. And if we looked at the other ones, if we looked at the other log streams, then across all 4 of them, we would see that the 10 messages were actually 10 orders were processed. So that's an illustration A of the scaling that's done on the consumer side. It also conveniently proved to us that the order in which the messages are received by the consumer is not guaranteed. It's unlikely that there was any duplicates received by the consumers. That's a very rare occurrence, but the ordering certainly um, is never is very rarely what you'd expect it to be. Okay, so don't need to look at that. This is on the consumer side. So, okay, what I am actually doing in the consumer, and I kind of conveniently ignored it, is I am checking that the structure of a message is is valid. Okay, I'm just doing some basic validation on the structure. And if the structure is not valid, I'm using the AVJ library that we used a couple of weeks back for to take care of that for us. And if the structure of the message is not valid, then I'm throwing an exception. And I'm kind of posing the question here, well, like who actually catches this exception and deals with it? Because that's one of the consequences of changing from a synchronous mode of communication to an asynchronous mode of communication. When you're using an asynchronous mode of communication, your client, which typically would be, a mobile app or a desktop app, it it's not going to receive any exception errors uh, in an asynchronous kind of architectural model. But somebody has to deal with it. So, and that's, as we'll see, there is a technique built in to SQS to deal with these scenarios. But for now, okay, all I'm showing you here in this screenshot is when I ran this myself, it did actually create 5 concurrent uh, instances of my consumer, and I have 5 log streams here. And when I looked at the detail, I saw that, the messages were not in any particular order. So we don't need to look at that. Um, Controlling concurrency. So if we decided that really for this consumer, there should never really be more than 2 concurrent instances because I'm never going to get such a high volume of messages that will need more than 2 concurrent instances. And that's a calculation based on how long you think it will take your Lambda consumer to process a message and how many it can process within that upper limit that's associated with a Lambda execution. I think the upper limit we said was 15 minutes. Now we're going nowhere near that, but so either way, you do a calculation and you determine that there will never be a scenario when you need more than X number of concurrent instances of your consumer. And so you want to configure that. And I'm showing you here how you do it. So there is a setting that you associated with the SQS event source, this max concurrency setting. So if I just quickly demonstrate that, if I go into my CDK code, and if I uncomment this, the lower limit is 2. You cannot set it to 1. So we're setting it to low as possible. So I do another CDK deploy, and I can be guaranteed this time that it won't actually create our case, it created four, as it turns out, but it certainly won't create anything more than two. I'll just do a cleanup of here first. I don't like this now because it looks like it's really slowing down from a deployment. Okay, good. And if I send my batch of messages again, or trigger the sending of the batch of messages, again, there's a bit of a delay on the consumer log group. And if I now go into this consumer log group, now the problem here now is that some of these are actually legacy, even though I requested the deletion of them. There's a delay in the deletion. Let's just do a refresh. Okay, and now these are the two new log streams. So that, for me anyway, that confirms that max concurrency setting is actually controlling the scalability of my consumer. Okay, moving on. This is just something explaining something that's going on behind the scenes. So I talked about the fact that the consumer is responsible for deleting messages and all that kind of stuff. But what actually happens kind of behind the scenes is that uh, when the consumer, which in our case is the Lambda service, when it polls for messages and the SQS service picks a batch from the queue and uh, sends them to the consumer, it doesn't actually remove the messages from the queue. What it does is it sets a timer called the visibility timer. And that timer um, makes the batch of messages that it has sent to the consumer, it makes that batch invisible to any other consumer that may request messages in the meantime. Remember, I spoke there a while ago that originally the idea was that you could have multiple consumers uh, polling for messages. So the way the SQS service kind of ensures that not more than one consumer will actually receive the messages is through uh, this visibility timer that's set. So kind of what we're showing here in the image, and again, is taken straight out of the documentation, that if for any particular message that has been polled by a consumer and provided to that consumer, the visibility timer is started, sorry, and while that visibility timer is timing down, that message cannot be provided to any other consumer that may poll it in the meantime. Now that the visibility timer though is there's a limit on it, obviously. I think I'm saying up here the default is 30 seconds. So if the consumer that actually received the message does not process the message and request the explicit deletion of it within the visibility timeout period, which by default is 30 seconds, if that does not happen, then the SQS service will now make that message visible again to other consumers. So the idea is, that's actually how it deals with multiple consumers, which admittedly we're not really dealing with. Now, don't confuse multiple consumers with concurrent Lambda instances, because the consumer, in our case, in our demos there, the consumer has been the Lambda service. There is only one consumer. We could, of course, if I just go back to here, uh, I could have an EC2 instance up here, which is also interested in messages in this queue. So it would be polling it separately. And so in that case, what we do not want is for our Lambda service to receive the message and the EC2 instance to also receive the same message concurrently. Maybe the Lambda service, though, so okay, that's what we want to try and avoid, and that's what the visibility timer is meant to deal with. But if the visibility timer expires, then that message is now visible again, and it's available to whatever consumer happens to request a batch of messages next. Okay, so that's again something that's happening behind the scenes. So within this visibility timeout, the consumer that receives the message has to A, process it, and B, request the explicit deletion of the message. It has to achieve all of that within the timeout period. Now, of course, you can control the timeout period of the visibility period. But I am saying down here, do I mention it? If you set the visibility timeout to be too high, like you might set it to a number of minutes or even hours, then that would mean that messages, the consumption of messages is going to be delayed because of that. If you set the visibility timeout period to be too low, then you have the potential that a message will be consumed by more than one consumer. So, it's a balancing act. And again, you determine the timeout, the visibility timeout period, again, based on your typical kind of message frequency and volumes. Again, obviously, we could configure this. When we create our queue, we could configure the visibility timeout period, but I don't get involved in that actually. I don't need to. Now, I posed the question, if I go back to here, when my consumer cannot, for whatever reason, there are two reasons why a consumer might not be able to process a message. One, it finds something wrong with the message and it throws an exception. Or two, if your consumer cannot process the message within the consumer's own time limit, because when we create a Lambda, you might remember, when we create a Lambda, we can set a limit on how long we're giving that Lambda to complete its processing. Processing in this case will be processing a batch of messages. So, and maybe the consumer needs to communicate with other services in order to do its processing. And those other services are slow in responding, or they're not available, or they respond with a throttling error. Any of those is going to affect my consumer. And so that might cause my consumer to not be able to process a batch. It may throw an exception explicitly, or it may just time out. And if it times out, then the Lambda service is essentially going to throw the exception on its behalf. So either way, my consumer, for whatever reason, cannot process a batch of messages and an exception is thrown. How do we actually deal with that within the confines of SQS? And so the answer is to create what's called a dead letter queue, or DLQ for short. And so the image on the right is again kind of explaining the scenario. Here's my consumer. Um, okay, something I didn't explain when I was talking about the visibility timeout is that it's possible that my consumer, so my consumer receives a batch of messages, doesn't process them within the visibility timeout period, then that means that that same batch or some of the messages in a batch might be received by the same consumer again. So there are retries happening on batches of messages. That's another part of the inbuilt design of the SQS service. In other words, it's giving the consumer a number of goes at attempts at processing batches of messages. But we want to put a stop to it eventually. Um, and also, there is the scenario where the consumer explicitly throws an exception for the reasons that I kind of mentioned earlier on. And so, whatever the nature or the cause for a batch of messages not being processed, then we want those messages to be sent into another queue. Now, the SQS service will take care of that. And this other queue, which we refer to as the dead letter queue, it's going to contain batches of messages that our consumer could not deal with for whatever reason. And you would then have a consumer associated with this dead letter queue. It's an ordinary queue. It's just that it is linked to this one, and so its role is defined, classified as the dead letter queue role. And the processing that's done by the consumer here, that depends on how you want to deal with batches that could not be processed. That's specific to the particular application. And so that's what I'm talking about here. So there's a setting called the maximum receive threshold. That's a property of this queue here. Like if you didn't have this DLQ option available to us, if the SQS designers didn't actually provide this DLQ option, then potentially my consumer is going to be repeatedly receiving the same batch of messages over and over again to process. And clearly that's not clever. Okay, we want to set an upper limit on how many attempts we want to give our consumer to process a batch. That's what's referred to as the maximum receive threshold. And when that threshold has been reached, then that is what causes the SQS service to decide, I'm actually now going to send that batch to the dead letter queue, and it will delete them from this queue here. Okay. I'm saying here it's useful for debugging in the sense that, it's kind of natural that messages may be written to this queue that are uh, not formed, not structured properly, or contain invalid property values, Um, so that you always need to consider that possibility, and we need to have a way of dealing with it. And this DLQ is the way we deal with it on the AWS platform. Separate consumer required. Okay, that's all right. So to illustrate this, what I decided is to declare DLQ for my original queue, my orders queue, and in my Lambda here, my consumer here does validation of the orders, and if it receives an order that's invalid, then clearly we want that order to finish up in the dead letter queue. Although it's not going to work out that neatly in the sense that what my Lambda here is going to receive is a batch of orders. And even if there's only one order within that batch that's invalid, the entire batch is going to be written to the dead letter queue. That's just the way the SQS service works, unfortunately. And again, it's probably because the SQS service was designed, quite a while ago, and that was the nature of the kind of issues that were arising back then, so to speak. So there could be, for our particular scenario now, there could be a batch of orders written to this dead letter queue. There will definitely be one order within that batch which is invalid, but some of the orders will actually be valid. And I suppose, strictly speaking, what this Lambda here should do is it should filter out the good ones and put them back into this queue. I don't bother doing that, but it's straightforward. We know how to do it anyway. We know how to write to a queue. All I'm getting this Lambda to do is, again, just standard console logging of all of the messages that it receives from this queue here. Okay, so how I set this up is now I'm conscious of time actually. What I might actually do now is maybe stop at this stage and pick up the story the next day to deal with the DLQ situation. Okay, I didn't pause for any questions, but whether there are questions on this topic or maybe on the assignment or anything else, I'll just give people an opportunity if they have any questions. No? Okay. In the meantime, you're probably working on the assignment really, but there is a lab which we just quickly go into it. So the lab actually has an S3 bucket. So I'm using the AWS CLI to upload an image to an S3 bucket. The S3 service actually sends a message to an SQS queue when that event occurs. And then I've got a Lambda that's processing the messages in this queue. Yeah. And then I start introducing SNS. Now, I know I haven't started talking about SNS yet, but certainly for the coming week, you should complete this part here. You can go on into the next part as well, and even all of it. You can do all of it, even though because it's all kind of cutting and pasting. And I try to explain what's happening as we work our way through it. But I will cover SNS fan out pattern formally, maybe even next week. I don't cover the SES service in any of the lectures. SES stands for Simple Email Service. I just show you how to get a Lambda to trigger the sending of an email. The way we actually do it, or the way I'm using it in this scenario, is when an image is uploaded to an S3 bucket, I want an email to be sent out to the user just confirming that we have received their image and processed it. So work your way through this lab, and you will be submitting this lab for assessment, although I probably make the completion date maybe not even next week, maybe the following week. Okay, I'm going to leave it at that for now. It doesn't seem like there are any questions, so I will be in touch with you again next week. Bye-bye.